Hello and welcome to question 4 in this walking talking mock covering the high demand questions for electric circuits. So question 4. A 12 volt filament bulb is connected to a 12 volt power supply. Not sure what that Z's doing there. The graph shows how the current changes after the bulb is switched on. So the current in amps, time in seconds, very small amounts of time in seconds, we can see here. After 0.10 seconds, the bulb works at its normal brightness. What is the current through the bulb when it's working at normal brightness? It's worth 1 mark. Okay, so I'm looking for the current after 0.1 seconds. Okay, so what they're asking you to do here is read a graph. I'm going to use a red pen just so it's a bit easy to see. 0.1 seconds, which lots of students will go and find that bit there. Okay, careful, 0.10, not 0.01. 0.10, so we're looking there. What is the current then? Whenever you're using the graph, whenever you're using a graph to do something like this, always draw lines. It's the best way to make sure you get it right. So it goes up there and then across there to the current. Okay, so if this was worth 2 marks now, we've already got 1 mark just by doing that. So now I've got to read off the current. I'm just going to check. I'm going back down to the bottom here just to see. It's easier going from 0 up to see what the scale is usually. 1, 2, 3, 4, 5. So each one of these is 0.1. So 1.6, 1.7. Yeah, so 1.7 amps. 1.7 amps. Okay, nice easy one to start. The bulb works at normal brightness for 30 seconds before it's switched off. Whenever they give you numbers now, they're going to be useful. Before it's switched off, calculate the charge. Okay, so it's a calculate question. So I'm looking at the charge that flows through the bulb in the 30 seconds before it is switched off. Give the unit. Okay, so 30 seconds. So I'm just going to put over here, it's worth 3 marks. Okay, so what do I know? Well, I know T is equal to 30 seconds. I know current. It's a tricky one here because it might well be that you didn't get this right. Don't worry about that at all. There's something called error carried forwards. And what will happen is you will always, even if you've no clue here at all, just make a number up. That's why this is quite a nice way of doing it, because now you can write I is equal to, because hopefully you remember that you're looking for Q equals IT. Okay, charge is Q, measured in coulombs. We'll put that down in a second. In fact, coulombs is someone's name, so use a capital C. Q equals IT. Even if I didn't have a clue for this question here, I could just write 1 there, 1 amp. That's fine. I'd get the mark for it then because I've identified the value I'm going to use. So Q is equal to 1.7 amps, and it's not milliamps or anything else. I'm just checking. No, that's good. 1.7 amps. So 1.7 times 30 equals, and the coulombs will give me the 3rd mark. So this was actually a much easier question than I originally thought. So 1.7 times 30 equals 51 coulombs. Calculate the energy transferred by the 12 volt bulb when it is working at normal brightness for 30 seconds. Okay, so normal brightness, so that tells me, so as soon as you see normal brightness, because they asked that in the first question, that's the clue there. This must be I equals 1.7 amps again. So what do I know? I know V is equal to 12 volts. I know T is equal to 30 seconds. And I know I is equal to 1.7 amps. Now, there's 2 ways of going about this question. Normally you'd have a lot more space below. I've condensed it just to make it fit the page a little better. Either you remember that power is equal to VI. In fact, the way I always remember it is VI equals P, VIP. So power is the energy in 1 second. And if you know that, then you will know that power times time is energy, total energy transferred. So power is energy in 1 second, and this lasts for 30 seconds. Or you might just remember that energy is equal to VIT. Okay, so power times time. And you've got 3 values here because they told you it's working at normal brightness, so the I as well comes in there. Lots of students might do 12 times 30, I suppose, although if you're doing higher tier, probably not. So 12 times 1.7 times 30. Okay, so we've got 12 times 1.7. 7.7, I can't type. 12 times 1.7 times 30 gives a total of 612 joules transferred. Between 0.02 seconds and 0.08 seconds, there is an increase in both the resistance and the temperature of the metal filament inside the bulb. Explain, in terms of the electrons and ions inside the filament, why both the temperature and the resistance increase. Worth 2 marks. 1, 2. So I'm putting my 2 bullet points in straight away. So why is it there's an increase in both the resistance and the temperature of the filament inside the bulb? Okay, well, we know that when the current increases, there's going to be more energy transferred. Okay, so that's going to increase the temperature. So why both the temperature and the resistance increase? So let's say as current increases, the temperature of, let's say, filament increases. So ions, these are the bits, the atoms inside, but of course their electrons can move. So move or vibrate. When things get hot, they vibrate. More quickly. Okay, so they vibrate more quickly or faster. As ions vibrate more, electrons collide with them more easily. This is known as collision theory. That's how resistance happens, really. The electrons, they move through the filament. They're knocking into things. So I've used the words electrons and ions. As ions vibrate more, electrons collide with them more easily, and resistance increases. Okay, because they can't move as easily. So because of those vibrations, because of those collisions rather, they're knocking into them. So if you can imagine, if you were walking down a corridor full of students, much smaller students than you, if those students were banging around and sort of running from one side of the corridor to the other, it'd be much more difficult for you to get through, and you'd probably take longer to travel through it from one end to the other. Whereas if those students were really still, low temperature, low energy, low internal energy, then it would probably be much easier for you to walk through, and you get through much more quickly. Okay, hope that helps. Take care. I'll see you for the next question in a moment or two.